video, I'm going to give a few more examples of the fundamental theorem of calculus, part 1. This is the application where I'm finding definite integrals by looking at the net change in the antiderivative. So it's always the case that in order to compute this definite integral, I know that it's going to be equal to the net change in an antiderivative function, capital F of 4 minus capital F of 1. And the only trick is that I have to find out what f is. F is the antiderivative of x to the negative fourth. So in my scratch work, I can say to myself, f of x is equal to x to the negative 4. And so I want to find an antiderivative function that gives back this value of x to the negative 4 when I take its derivative. And I can use power rule for antiderivative in order to find this. I know that my antiderivative is going to be of one higher power because when I take its derivative, that power drops down. So negative 4 plus 1 is negative 3. But then I have to worry about the coefficient, that I need to be able to get rid of this negative 3 when I take the derivative. So here's an antiderivative, and let's check. I think it's always worth checking. I claim that this is the antiderivative. Let's go ahead and take the derivative of this function to see if I get what I want. The coefficient stays out front. By power rule, the negative 3 comes down front. And also by power rule, the exponent drops by 1. And negative 4 is 1 less than negative 3. Multiplying the coefficients, I say negative 1/3 times negative 3 is actually 1. And I get the value that I wanted. So we just found out that our antiderivative function in this case is negative 1/3 x to the negative 3. So I evaluate this net change of the antiderivative function by saying, oh, that's negative 1/3 of 4 to the negative 3 minus, being careful of signs, negative 1/3 times 1 to the negative 3. And I can simplify each of these. Let's see. 4 to the third is a big number. It's 164. And then 164 times 3, all negative, is going to be negative 1 over... I should have a calculator and I don't. I'll pause this. So 4 to the third is 160, or is 64, because it's 4 times 4 is 16 times 4 is 64, and then I multiply that by and I get 192. So I have negative 1 over 192, and then this, the negative and the negative cancel to become addition, and 1 to the negative 3, it doesn't matter, 1 times itself however many times is still 1, so I end up with that plus 1/3, and I can get a common denominator, and I find out that this combined fraction is going to be 63 192s. Here's another example of a definite integral, only this time the function in the interior is one that's difficult to find an antiderivative of just algebraically, that we're going to have to analyze going on graphically because this is an absolute value function. So first, I'm going to draw what does the function x squared minus 1 look like. Notice that it has intercepts at both 1 and -1, because that's when my outputs would be equal to 0. It has a y-intercept down at 1. So this green curve would be the graph, the function f of x equals x squared minus 1. But then when you take its absolute value, it takes all of the negative values and flips it over this x-axis. So I end up with this graph. And if I want to know what the integral is from the value of 0, 1, 2, 3, and you can see I'm finding area under the curve like this. So there are a couple of approaches that we could have. One approach, and the approach that I'm going to take, is I'm going to break this up into two separate integrals, because I know that instead of this, I'm going to think of this as the integral, using my picture as a guide. This is the integral from 0 to 1 of the negative of this function, because that's the place where it was under the absolute value, or under the x-axis. So when I take the absolute value, it's flipping it and taking the negative of it. And then from 1 to 3, I don't have to worry about anything. That's going to be the integral as written of the function x squared minus 1 dx. So now that I have this written as two separate integrals, let's actually compute each of these integrals. And I'll write that down over here. So the first integral is the integral from 0 to 1 of the negative of x squared minus 1 dx. I'm going to do a little bit of algebra and distribute this negative sign, so that becomes negative x squared plus 1 dx. And the antiderivative of this, using antiderivatives, I see that it's going to be negative 1/3 x plus x evaluated from equals 0 to 1. Now this is notation that we haven't used yet, and I think it's a compact way of being able to explain what's going on. So this is my f function. This is the antiderivative of my f function, and I can check because when I get the derivative, I get back to what I wanted. And this is saying that I want to evaluate it from x equals 1 to x equals 0. When I do that evaluation, I'm looking at the net change of this antiderivative function. And in this case, it's 1/3 of 1 cubed plus 1. That's where I plugged in 1. And I tracked out negative 1/3 of 0 cubed plus 0. So this first term, 1 cubed is just 1, so I get negative 1/3 plus 1, and then I subtract off 0 plus 0, which is actually just 0. So I see that this first integral gives me a value of 2/3. So that's what this area right here is. It's an area of 2/3, because that was this first integral. Now I'm going to go ahead and compute the second piece of this integral in a similar fashion. So recall the second piece is the integral from 1 to 3 of x squared minus 1 dx. So I'm looking for an antiderivative of this function. In my shorthand, I know that the antiderivative of this is 1/3 x cubed minus x, and I can take the derivative to check. And again, using that compact notation, this is going to go from an x value of 1 to an x value of 3. So my net change is going to be 1/3 of 3 cubed minus 3 minus 1/3 of 1 cubed minus 1. Of course, we plug in our upper bound and then subtract out the lower bound. Because we want to know what the net change is, I would get the negative of my net change. So what is this? 3 cubed is 27 divided by 3 is 9 minus 3 minus 1/3 minus 1. 9 minus 3 is 6. 1/3 minus 1 is negative 2/3, so I get plus 2/3. So this is the same thing as 18/3 plus 2/3, which is 20/3. So that tells me that this second integral was equal to 20/3, was equal to 2/3. This combined area is going to be equal to 22/3.